Page 2 of normal distribution. Number 7. The weights of babies born at Prince Louis Maternity Hospital last year average, which is mean, 3 kilograms with a standard deviation of 200 grams. If there were 545 babies born at the hospital last year, estimate the number that weighed less than 3.2 kilograms. This is a pretty normal problem. The only thing that's slightly challenging is the fact that they use 3 kilograms here and they use 200 grams here. They're different units, so we need to combine these two. There's nothing in the formula booklet that tells you the difference between kilograms and grams, so you have to memorize that. There's 1,000 grams in each kilogram. So 200 grams is actually equal to 0.2 kilograms. So we're going to see this when we draw the little standard, the normal distribution. But whenever you do one of these problems, even if they don't ask you to draw the picture, please draw a picture. To help you out on the problem set, I've always put these little curves here. So of course the mean is 3 kilograms, like they said, right? And they said that the standard deviation is 0.2 kilograms, so each one of these is 0.2. So this one would be 2.8, this one would be 3.2, this would be 3.4, 3.6, and 2.6, and 2.4. If there were 545 babies born at the hospital last year, estimate the number that weighed less than 3.2 kilograms. So, oh, what a coincidence. It's right on top of a standard deviation line. So we can do this using the estimate of 68, 95, 99, right? So remember, with 68, 95, 99, we know that this is 34. We know that this next section is 13.5%. The next section is 2, and the last one is 0.5. So basically this is 50%, exactly half, plus 34%, right? So if we add these two together, that would give us the area shaded in here. So that would be 84%. That's it, okay? All right, next one, between 2.8 kilograms and 3.4 kilograms. We are going to do the exact same scale at the bottom, 3 kilograms, 3.2, 3.4, 2.8, 2.6, 2.4, 3.6. Okay, is that right? Yeah, 2.4 to 3.6. We are going to now find the probability that we're between 2.8 and 3.4. Again, what a coincidence. It is exactly on the standard deviation line. So we could use 68, 95, 99, right? Remember that the middle two sections are the famous 68%. And then this section here is 13.5%. So we could just add those two together. 68 plus 13.5 is, I don't know, maybe like 81.5. 81.5% for those three sections. All right, so not too bad, right? We're not even using a calculator yet. We're just making estimates using 68, 95, 99. Good practice. Number 9, the weights of Jason's oranges are normally distributed. Remember that whenever we have a normal distribution problem, this is one of the easiest problems to figure out the type of problem it is on the IB exam, because they have to pretty much say normally distributed as part of the problem. Otherwise, how are you supposed to know that it's normally distributed? So they have to say that. 84% of the crop weigh more than 152 and 16% weigh more than 200. This is interesting. They did not tell us the mean and standard deviation here. So how on earth are we supposed to figure it out? Let me give you a hint. 84%, 16%, we've heard those numbers before through 68, 95, 99. So why don't we first just take one of these and chop it up into 68, 95, 99. So we'll put 34s in the middle, we'll put 13.5 on either side, we'll put 2 on either side of that, and then we'll put the 0.5s at the end. We don't know what the mean and the standard deviations are here of Jason's oranges, but we do know that 84% of the crop weigh more than 152. And 16% weigh more than 200. So remember, 16% is like this chunk here, right? So 16% weigh more than 200. that means that since this here is 16%, doesn't mean that this number is 200, because 16% way more than 200, right? And then let's try to do the other one. 84% of the crop weigh more than 152. So let's see, 84 would be 34 plus 34 plus 13.5 plus 2 plus 0.5. If we add all of these together, it would be 84%. Do you remember from the last problem? 50% plus 34% is 84%, right? So 50% plus 34% is 84%. So that's how I kind of remembered that 84% is a number which can be found by summing up these sections from 68, 95, 99. So 84% is greater than 152. That means I put the 152 right there, right? So now we have some information here. We know that this point here is 152. We know that this point here is 200, right? From this, can we figure out what the mean is? Pretty easily, right? Because if the one standard deviation to the left is 152, one standard deviation to the right is 200, then there's a number exactly in the middle of 152 and 200, which has to be the mean, right? I think it would be like around 175. I think it's 176, right? How do we figure that out instead of guessing if we use the calculator? If we find the average between 152 and 200, that would be the mean. If we add 152 and 200 together and divide by 2, that would be 352 divided by 2. It would be like 176, I think. Okay, is that right? Yeah, 176. So 176 would be the mean. And then what would be the standard deviation? Well, remember, the distance between 176 and 200, the distance between 152 and 176 is the standard deviation. So if we do 200 minus 176, it gives us 24. So the standard deviation would be 24. So look at that. We figured out the mean and the standard deviation. They didn't give it to us. We figured it out because they gave us some clues about what percentages were above 200, were above 152. Okay, and just to make sure that you drew the drawing correctly, let's reread this and make sure that we did it the right way. 84% of the crop weighs more than 152. 84% weigh more than 152. Yes, that's right, right? 16% weigh more than 200. Yes, that's right. Okay, so we did it right. B, what percent of the oranges weigh between 152 and 224? 152, remember, is one standard deviation width to the left of the mean. And then 224, let's see, this would be 176. It would be the mean. 200 would be the next one. Remember that the standard deviation width is 24. So if we add 24 again, we get 224. And that's the right boundary they want. So they want to know 152 to 224. So if I color that in, you can see that it's got the middle section, which we already know is 68%. And it's got the neighboring section, which we know is 13.5%. If we add these two together, which if we remember from the previous problem, I think is 81.5%, that is the percentage that's in between 152 and 224. Okay? All right. Let's go to 13. A bottle filling machine fills an average of 20,000 bottles a day with a standard deviation of 2,000. We're back to an easy problem where they gave us mean and standard deviation, so a little bit easier. In the middle, we're going to write 20,000 bottles a day with a standard deviation of 2,000. So that means plus or minus 2K, right? So that would be 22K and 18K. And then if I added two more, it would be 24K. If I added two more, it would be 26K. And then we're already at the edge of our 6 sections that are visible. If we subtract 2K from 18K, it would be 16K. If we subtract 2 more, it would be 14K. We've written down everything on the number line. I think we're fine with that. Assuming that the production is normally distributed and the year comprises 260 working days, calculate the approximate number of working days on which under 18,000 bottles are filled. Okay, so like under 18,000, I would color that in. It looks kind of like this, right? And wouldn't that be 16% because it's the 13.5 section, the 2 section, and the 0.5? If we add those together, it would be a 16% probability, right? They want to know the number of working days on which less than 18,000 bottles are filled. It would be 16% of the working days. How many total working days are there? We're going to take our percentage, which is 16%. How do we write in decimal 16%? Isn't it 0.16? And then we're going to multiply it times the total number of working days, which is 260, and that will give us the number of working days on which under 18,000 bottles are filled. Okay, so now we're going to need the calculator. I'm going to flip it on. And I'm going to do 260 times 0.16. 16% is 0.16 multiplied. And the answer is 41.6 days. Now, on the IB exam, if they ask you for the approximate number of working days, we're going to round that up to a whole number of working days, so we'll say 42. Okay, 42 days. What about how many number of working days are over 16,000 bottles filled? And remember, if the middle is 20, then 16,000 bottles would be here. Over 16,000 bottles, so it would be all this. So the only thing that's not included is the 2% and the 0.5% that are to the left. So wouldn't that be 97.5%? So 97.5%, the decimal will be 0.975 times 260. Let's use the calculator again. 260 times 0.975. 253.5. 253.5. I would round that to the nearest number of days. 254. Notice that here we rounded to the nearest number of days even though it wasn't 3 sig figs. So, you know, I would say that on some of these, like for your IA, 41.6 I think kind of has meaning. You don't need to round it, but on the IB exam, usually if they say how many working days or how many people or something like that, they want you to round to a whole number of days usually. What about between 18,000 and 24,000? So 18,000 is here, 24,000 here. So 18,000 is here. This is 20, this is 22, and this is 24. So we want to know between 18,000 and 24. So that would be 68% plus 13.5%, which we already know from previous problems is 81.5%. So 81.5% times 260 would be the approximate number of working days on which we had between 18,000 and 24,000 bottles filled. So let's do that on the calculator too. It's 260 times 0.815, which is 211.9. which rounding would be 212 days. Okay, so I think we're done with page 2.